So let's take a look at logarithmic differentiation. So this is a technique that we can use to do complicated derivatives more simply. We're going to actually use logarithms to help us. So we're looking at this rather complicated function here. What I'm actually going to do is I'm going to take the logarithm, the natural logarithm in this case, of both sides. So if I do ln of y to be ln of the right-hand side, and I'm going to change the notation here to a 1/2 power. Okay, so the next thing that I can do is use all those log rules to help me simplify. So this would be ln of x squared times 3x minus 2 to the 1/2 minus ln x minus 1 squared, because the log of the quotient ends up being the difference of these logs. So now we'll do a log of a product as a sum of logs. And finally, we'll use the exponent rule from logarithms. Okay, so now we've simplified it as much as possible with our logarithms, and we can actually take the derivative. So realize nothing we've done yet has been aimed at finding the derivative. Okay, so now I'm going to take the derivative of both sides, because this is now an implicit differentiation. Okay. So when I do the derivative on the left-hand side, that's the derivative ln y. So what is the derivative ln y? Well, the chain rule in implicit differentiation tells us that that's 1 over y dy dx. On the right-hand side, this is just our regular derivatives. So we get 2 times 1 over x minus 1/2. Derivative ln 3x minus 2 is 1 over 3x minus 2 times chain rule factor 3 as the derivative of 3x minus 2, then minus 2 times the derivative of ln x minus 1, which would be 1 over x minus 1. Okay, so now let's clean this up a bit. Okay, and so what we want is we want dy dx, of course. So we're now going to have to solve for that. So I'm going to multiply y on both sides of the equation. Now, when we were doing implicit differentiation, we were okay having a y left in the result. But here, we don't need to leave a y there because we know what y is from the beginning of the problem. We have that y is this expression. So what I can do now is actually just substitute what was y and there we have our derivative. Okay, so that was actually a lot easier than doing all the quotient and product and chain rule that would have been involved in doing the straight derivative. So by using logarithms and then using implicit differentiation, I got my derivative. So let's go to another example, which is probably a better example because this is some place where the logarithmic differentiation must be used, because if you'll notice, with x to the x, I have a function of x raised to another function of x. This is a type of problem where I will need to use logarithmic differentiation. So let's take a look. Start out with y equals x to the x. Apply ln to both sides. Simplify using the logarithm rules. Okay, no derivatives yet. So now I'm going to start taking derivatives. Okay, so again, I've set up a implicit differentiation on the left there, but it's always the same here because I'm always doing the derivative ln y, so it's 1 over y dy dx. Now notice on the right-hand side, I have a product rule situation. So the derivative of the first is 1 times the second as it is, ln x, plus the first, x, times the derivative of the second, 1 over x. So now I can move over here, and what I can do is just simplify a little first. 1 over y dy dx is ln x plus 1. Multiply over the y and substitute back for what y is. Done. Let's look at another one. So if we're going to find the derivative here for this complicated function, so again, I'm going to apply ln to both sides. I'm going to rewrite that using a 1/2 power. All right, then I'm going to simplify using my logarithm rules. So I have the log of the numerator minus the log of the denominator, but in the numerator I have a product as well. So ln tan x plus ln 2x plus 1 to the 1/2 minus the ln 3x minus 5 cubed. Okay, now I'll use the further logarithm rules using the exponent. Okay, now I've simplified it as much as possible with logarithms, and I'm going to go ahead and take my derivatives. Okay, so taking these derivatives, still 1 over y dy dx over there. Here I have the derivative of ln tan, so derivative ln of something is 1 over something times the derivative of that something. So 1 over tan x times the derivative is secant squared plus, okay, constant multiple 1/2, derivative of ln 2x plus 1, 1 over 2x plus 1 times the chain rule factor of 2 minus 3 ln of 1 of 3x minus 5, 1 over 3x minus 5 times the derivative of 3x minus 5, which is 3. And then we'll just simplify this a bit. So secant squared x over tan x plus those 2's cancel out. And I'll get a 9 over 3x minus 5. And so what are we left with? So I'm going to do 2 steps in one here. I'm going to solve for dy dx, in other words, by bringing the y over, and then just substitute back what y was originally. So tan x times 2x plus 1 to the 1/2, or if you want to write it with square roots, okay. 3x minus 5 cubed, and whatever was left inside. And there's my answer. And that's logarithmic differentiation.